Okay, so we're going to be looking at module 2 which is belts and chain drives. Okay, last time that we were together, module 1, we looked at spur gear drive. So we looked at, the design of a set of gears, and we finished up that design. As you recall, kinematics sets us up for everything except for the forces. Okay, in machine design elements here, we kind of finish up some of those designs. So we looked at the kinematics of gears. So that was like, how many teeth are we going to use? What is the diametral pitch of it? How fast is it going to be rotating? What is the velocity ratio? If we have more than one together, what is the train value at the end? Which direction are they rotating in? And we just stopped there. Okay. Same thing with our belt drives and our sprockets, our chain drives back in kinematics. We've already looked at the kinematics of this stuff. So at the very beginning here, we're going to review a little bit of that because it's been a little while since we talked about it. So I want to kind of bring that back to the front of our mind. But we're going to then kind of finish up that design. That's what we're doing here. So in module number 2, learning plan, you're going to notice that the learning plan is, I'm going to get myself off the screen here. The learning plan is going to be, first of all, we're going to be looking at the chapter. We're going to be going through and targeting the sections we need to in the PowerPoint presentation. Okay. Along the way, we're going to be doing some example problems, some practice problems, and I'll alert you to those that you want to add to your notes so that you'll be handing those in to be graded. Then what we're going to do is we're going to use, and I kind of have it down here, starting with example number 2, we're going to use the Gates catalog. So a vendor and like an industrial vendor catalog to specify the drive. Okay. And we're going to be going through that process. So right here I have, if you want to download it now, because we're going to be referencing it later on, this is the PDF of their manual. I have the paper, the sheets kind of printed out that we need, and I'll bring those in, but I'll give you a chance to catch up through that PDF. It's like a 300+ page PDF just because it's their catalog of all their stuff. And then we're going to be doing the design of a chain drive. But in this case, the chain drive, we're going to be using the book information for. Okay, the book information. Now, down below, you're going to also notice that we have 2 Excel spreadsheets. One is going to be for the V-belt drive, and one is going to be for the chain drive. Now, if anybody had me for computer programming, and some of you did, okay, we did the chain drive Excel spreadsheet. So you're going to notice that that is very familiar. All right. And that should be almost identical, except you guys made it fancier than what mine is, but that's okay. So, so you'll kind of look at that and see that that's going to be familiar to you. If you want to use the one that you made from computer programming, feel free to do that. But if you didn't have me, which there's a number of people who didn't, then I've got it here for you. Okay. Then you're going to submit your practice problems to me, and those are due at the end of this week. And then also assignment number 2. So we'll be looking at that at the end. Assignment number 2 is going to, kind of be similar to the examples that we're going to be doing at the top, but you can use the Excel spreadsheets where they're applicable, for instance, okay, to kind of automate that process. Okay, so if you need to, go ahead and download the items that you see here. I'm going to start by pulling up our PowerPoint presentation, and I'm going to download it first, as long as I have it here, and then I'm going to pull it up as a PDF. Over here, there we go. Oh. It's down. Okay. I don't know if I like this. Everybody ready? I know I asked you to do a couple things. Okay, so let's look at chapter 7 in our book. Our chapter 7 is going to start on page 244. On page 244. And like I said earlier, it's going to be on belts and chain drives. We're going to specifically be looking there. Now, at the beginning here, it's talking about the big picture. And the 2 items that we're looking at specifically in here are those belt and chain drives. And a belt drive is going to have similar applications to gears, except we're going to find that it's going to have the flexibility of center distance, meaning that you can kind of make it wider or closer, and we don't have to have the belts really close together like we did gears. The gear teeth had to be in engagement, and then the center distance was set by the size of the gears. Okay. And it's great for, number one, pushing through really high torques. Number two, having a nice compact design, but sometimes that might work against us. Okay. Because we want to have some flexibility of where that center line is going to be. So belt drives and chain drives offer that flexibility. Okay. Now, when we look at when to use what, we're gonna find out as we go through, typical applications for belt drives are going to be when we have higher speeds and lower torques or lower horsepowers that we're dealing with. Okay. When we're looking at a chain drive is going to be, again, similar application, except because of the way that it's structured, we're going to have the ability to push through higher loads, transmit higher torques, higher horsepowers. And so you start looking at chain drives for those types of applications. And normally they're going to be a little bit slower on the speed. So if we take a peek at figure 7.1 in our book, and I'm going to go underneath my camera, and this figure is at the top of page 245. Okay, so if you open up your book, you'll see this more clearly. Now, in this case here, we have kind of a pictorial view, and then we have a, kind of a straight on view. And what we have is a drive system. And this drive system is made up of 3 different types of drives, okay? One of which we've already talked about. So this green portion in the middle, this is an enclosed gearbox, okay? So we already talked about gears. So that's one of the power transmission elements or the drive system elements that we have here. The next one we're going to see, we can see it over here kind of, but it's a better view on the right-hand side, is going to be a belt drive. Okay. And a belt drive, you'll notice, is going to be attached to our motor, and it's going to then be the input on the actual gearbox itself. Okay. So we're going from motor to the gearbox with a belt drive. Okay. Sometimes we can go directly to the gearbox with a motor, but in this case, they're using that belt drive in between. Now you'll notice that they have a smaller sprocket on the motor and a larger sprocket on the gearbox going in. So we're slowing this down a little bit, okay, based on the size of those pulleys. And we'll be looking at those kinematics early on here in the chapter. Then you'll notice on the backside, so it goes through the gearbox then, and then on the output of our gearbox, which would be a shaft, we don't really see it coming out here, there would be a small sprocket, which is going to have then a chain attached to it that is going to engage with a larger sprocket that's going to be on our output machine. So in this case, we have 3 different, distinct drive types to accomplish going from our drive motor, which would be a high speed, low torque application, all the way to probably a larger machine that needs more torque, more ability to do work. And we've reduced that speed, a couple different times here for sure. Okay. So you can use these drives in combination with one another. It doesn't mean that, if I do a gearbox, I'm dedicated to that gearbox. All right. You can see here that you can utilize these to, kind of, account for whatever type of application or the center distances. When we have gearboxes, as you can see here, and we don't see the gears on the inside, again, it's got a compact design, which can be advantageous, but it also is not flexible and it's rigid on center lines, okay? Where now with belt drive and chain drives, we have some flexibility there, okay? Go back to my PowerPoint. Yes, you can. Where did my, oh, here it is. Here's my, but all the way over there. What do you notice is different about the belt and the chain drives compared to the gearbox? And maybe I already kind of alluded to the big one. What do you notice is different in those applications? Yes, the center distance is the big thing. Anything else that you notice? We don't see the gears here, but we know about gears. What else? Yeah, the gearbox is enclosed, and most often we're going to have chain drives and belt drives. They're going to be, out kind of in the open, or at least guarded if they need to be. Why would we use, any idea why we would, I'm pointing at something you're not seeing. Why would we use a belt drive on the input, even before we talk about belt drives? Why would we use that one there? What would you suspect? Just kind of knowing what you know about belt drives, or even just looking at this application. Why do you think a belt drive is on the input?
Here and they kind of, you can put the motor pretty much where you want it.
Well, I can do that with a chain drive too.
I thought you said, yeah, it allows pitch.
Oh, this is a synchronous belt. The synchronous belt has little knobbies on it. Yeah, it does. But that is an advantage of a V belt, which we'll be looking at. So if we have, like, for some reason, if we get a jam in our output machine, right, that belt can slip, right? Absolutely. Yes, that is going to be an advantage. Any other thing that's kind of going on here related to, like, the rotations on the input to the output? Where is it faster? On the motor side, yes. So belts are going to normally be on those faster linear speeds than what chains are, okay? Why do you think that is? Yes, sound is a big deal, right? And also vibration. These are going to vibrate a little bit less based on the materials that they're made out of. So, so usually on that high speed side of things, if you need, if you're considering and you need the flexibility of exactly what you had talked about, belt drives are usually going to be on the higher speed side of things, and then your chain drives are going to be on the lower speed side, okay, where there's more torque and lower speeds that you're going to be dealing with. Okay, good. So that's kind of just an overview right now. Why do I feel so? I don't know what I'm doing here. Okay. I want to ask this question too. Where do you see belt and chain drives, like, out in the world? Like, what applications do we see belt and chain drives that you might come across, maybe not on an everyday basis, but, in typical applications? There's a belt in your car, a serpentine belt in your car. Absolutely. What else? Say it again. On our bike. Yes, we've got chains on our bike. Yep. Snow blowers. What else? Oh, it's all over the place, right? Chains and belts. Yep, for sure. Good. Yep. Awesome. Good. Anyone else? And I'll even look virtually. If you guys feel free to put in the chat. I'm going to pull the chat out. So if you guys do have something, I want to make sure you get your voice heard. So feel free, for those who are virtual, to add to it as well. Okay. All right. So they are around and about, and we use them a lot in machine design to to transmit not only rotational speed, but also torque, and be able to do work. Okay. So the objectives of this chapter, we're going to be describing basic features of belt drive systems. We're also going to be looking at different types of belts and kind of identifying where they would be most often used. And then we're going to use a manufacturer's catalog, a Gates catalog, in order to specify a belt drive. And then we're going to kind of do the very same thing with the chains, except the chains, we're going to stick to the textbook information, mostly because chains are kind of like a standard category, kind of like fasteners. If somebody's going to make a chain, they got to make it to certain specifications, if, based on the number that it is. And it has to have, all the same types of tensile strengths and such. They might go off and have maybe some different types of, off the shelf or their specific type of brand of chain. But if they're, calling themselves a roller chain manufacturer, it's kind of all standard. That's why we're using the textbook information, because then it would, if you wanted to use a vendor, they're going to be very similar. Let's talk about the kinematics of belt and chain drives. So first of all, as we said earlier, those chain drives are going to be on that higher rotational speed. They're going to be quieter for us. And then the chain drives are going to be on the lower speed but higher torque, and just the opposite for belt drives. Chain drives are going to be a little louder and not as quiet, where belt drives will be more quiet. but they always say that they are flexible drives. And I think we already hit on this, but why are these flexible? Why do we identify that these are flexible? Why are these called flexible drive systems? Gears aren't. They can stretch. You've got that center distance that you can make variable, you know, and so they do have the ability to just fit more applications, especially when we talk about distances. Oh, belt drives are used on a table saw. Thank you, Jonathan. Now, as we look here, we're gonna open up to page 247 and look at illustration or figure 7.3. Okay. I've got my chant box down here. I'm gonna scooch it down here. Now, down here, this figure on the bottom of page 247 shows us kind of 3 different types of drives and how they actually transmit rotational speed and torque. So over here on the left-hand side, this is going to be a chain drive, all right? Now, a chain drive is going to have the individual chains here, and then up through the inside, our sprocket is going to have teeth that are going to fit, okay, in there. Now, I happen to have some chain and sprocket items here. Now, in the classroom, I'll kind of pass these around, but I'll pull these and I'll put them underneath the camera right now so we can kind of see. So this is a chain, okay, and we can kind of see, and I'm pretty certain everybody has seen and experienced what chain looks like, but my chain is going to be sized so that it fits over the teeth of a sprocket. So the sprocket and the chain go together, okay? They have to, you know, be the right size teeth to fit up in the middle of each one of those spaces that are provided between the rollers on the chain, okay? So when we're specifying a chain drive, we're specifying the sprocket. This is called the sprocket when we have a chain drive. And then we're also going to be specifying the chain, how long it is. And then we're going to be counting these pitches. This is a pitch, a pitch, a pitch. Now, as we look here, you'll notice that they have the dimension for the pitch diameter. The pitch diameter, just like for gears, is going to be what we call that effective diameter on our sprocket in this case, okay? And so the pitch diameter will always be given to us, you know, by the manufacturer. Right? When we have a synchronous belt, okay, a synchronous belt is one that is going to have these teeth on it, and then the pulley is going to have the same type of teeth. Now I have a really big one in here. I'm not gonna be able to pull it underneath our camera, but here we have synchronous pulley, and you'll notice that it has, if I can, you guys can kind of see that, maybe. Okay, you can see that there's places for, or little grooves in here for the teeth on our belt to sit in, okay? So I've got that here. So I know you're not on camera, you might not be seeing this, but this is our synchronous belt. I don't know if you can really see it, but those fit into those grooves on our pulley. So I'm going to keep this up here. If anybody wants to kind of grab it and look at it, but it kind of gives you an idea of what a synchronous drive, you know, would look like. And then it's going to have a similar feel belt-wise, but it has these teeth on the inside. Now, a V-belt drive is going to be this one. Now, here too, we can kind of see, I don't know if you can see it on the screen very well, but there is a V on either side here. It snugs down into a groove that this fits into on this pulley. Okay, so this one is another type. Now, the V-belts, I don't know which is more popular nowadays, but to size them, synchronous belts and V-belts, it's just going to depend on, do I need timing or not? Meaning, do I need kind of the benefits of a gear drive in order that I don't want my belt to slip. And I also want it to be timed so that it's going to be the same, you know, cycle after cycle after cycle. On the other hand, when I have a V-belt, because there's not teeth in here and it's just the groove that it's sitting in, as mentioned earlier, I think it was by Hunter, he said, you want that to slip potentially if you get an overload situation. And that's by design, it's easier to have that belt slip than to break anything on the other side that's much more expensive, okay? So depending on the application that you're looking for, you know, again, their construction is going to be very similar. They're still considered belts, but the applications are going to be different. Okay, they're going to be different. Now, let's see where we're at here on our PowerPoint. Now, the kinematics, right? So many of you have had kinematics very recently with me. Some of you, maybe it's been a little while. So it's worth our time to just kind of relook at some of the familiar equations, but then also kind of take it a little bit further as well. So the kinematics, if we look at figure 7.2 at the top of page 247, that very same page, we're gonna go just down over here. You'll notice that we have a rotating disc, okay? The rotating disc has a rotational speed of WA. We call that the angular speed or the rotational speed. Most often this is given in RPMs, right? How many revolutions per minute is this rotating at? And it's going to be rotating about a center, right? Now, you'll see that there's also this straight line velocity component. Back in kinematics, we call, well, you tell me, what do we call that back in kinematics? They don't call it the same thing in this book, but it is the same. Remember what we call that? The straight line started with a T. Tangential speed. Okay, we calculated tangential speed. We calculated radial speeds. Okay. Did that just like come out for some reason? Or you were like, I was kind of guessing. Yeah, so tangential speed. Tangential speed is going to be the straight line velocity component associated with the rotating speed that we have here, okay? So the tangential speed or the straight line velocity, or what they're calling the linear velocity component, will always be perpendicular to its radius back to its center of rotation, okay? And in the direction of rotation. Now, if you remember, and I'm sure this is going to sound familiar because we use this a lot back in kinematics, V is equal to R times W. Straight line velocity is going to be equal to the radius of that point from its center of rotation. So this radius right here multiplied by the rotational speed. But could we put RPMs directly into that equation? No. What do we need to change our RPMs to? Radians per second. So we're going to see us change it there too a little bit later. They don't show that down here, but in order for this to be used in this equation, this has to be in radians. We can't have it in RPMs. But as you recall from kinematics, we're going to be given rotational speed and problems in RPMs. And when we report it out, we don't leave it in radians per second or radians per minute, whatever it might be. We put it back into RPMs, okay? Because you're not going to go up to somebody and say, I want a motor that's rotating at blah, 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 radians per second. They're going to be like, yeah, that's nice. They want it in RPMs. Those are going to be the accepted terms, if you would, okay? Now, when we look at this radius, and we go back down here and we look at any one of these items, that radius is going to be half the pitch diameter. So when we're calculating for straight line velocity, for instance, which is going to end up being our belt or our chain speed, linear speed, we are going to need the pitch diameter, but we're going to divide it by 2 and use it in the radius of that equation. Okay, right? So that's how those are related, and just kind of remembering V is equal to R times W. V is equal to R times W. Now, when we have drives that are speed reducers, okay, and that's most often the application that we see. Most often, doesn't have to be though. A speed reducer is going to be when our input is going faster than our output. So a very typical gearbox design is I'm getting, rotational speed from a motor. It's high speed. I'm going to do some gearing down normally in the inside, and then my output shaft is going to be going much slower. Okay, that's going to be a speed reducer. In that process, what are we increasing? We're reducing the speed, but we're increasing torque. Exactly. So the benefit that we get from that is not just to get something slower, but we're going to be able to do more work. Right? We're going to be able to move something or rotate something that otherwise wouldn't have been able to be done when we had the really fast speeds. Fast speeds are going to be low torques. Lower speeds as we reduce those speeds and increase the torque, we can do more work on the end. So the smaller pulley most often is going to be mounted to the higher speed shaft, and the larger pulley is going to be mounted to the lower speed shaft. Now, we can have a situation where we have just the opposite, where we have a speed increaser and then we're going to actually mount them opposite. So the smaller pulley then is going to go on the low speed shaft and the larger pulley is going to go on the higher speed shaft. Okay. So it can go either way. Most often we're on the speed reducer side, but you can be a speed increaser. Now, that linear velocity, that V, is going to be uniform throughout the length of the belt and chain. So if we look at figure, I looked at 2. Yep, I looked at, oh, I want to see the layout down here. So on the following page, we see this illustration. So what this is showing us is really kind of a schematic, if you would, of a pulley. Now in this book, they usually refer to it as a shiv, but and they say pulleys or shivs. I've always said pulley. So this is going to be my belt pulley on the low speed side, and this is going to be my belt pulley, I'm sorry, on the high speed side, and my belt pulley on the low speed side. And you'll notice that this dark line going around the outside is representing the belt that is over both pulleys. Okay, that it's over both pulleys. When we look at belt speed, that's going to be V right here. That is going to be the very same number that as we rotate around here and we have straight line velocity, that's what the belt speed is going at. It's that V value. So back over here, this V is how fast that belt is going. Okay, so that's going to be an important number for us. Speed ratio. Now, when we looked at gears, speed ratios were pretty easy to get. And actually for sprockets, they're pretty easy to get. We count teeth. We can count the number of teeth on one gear. We can count the number of teeth on the other. We divide them and we get a speed ratio. And all that means is how often is one going around compared to the other? And most often you want to know, okay, how fast does that input, the high speed shaft or the high speed element, have to go in order to get the output to go around once. So we hear terms like 2-to-1 ratio, 5-to-1 ratio. It doesn't have to be an even number. It can be 2.5 to 1. Okay, but all it's saying is my input has to go around 2.5 times before my output goes around just once. Okay, now we saw this equation. We saw this equation right here when we were back in kinematics. We knew that we could calculate velocity ratio by either using and comparing the rotational speed of the input to the output, or we could compare the physical pitch diameters, or we could compare the number of teeth. Okay, number of teeth isn't available if we're using a V belt though, right? Because there aren't any teeth on there. But if we're using a synchronous belt, we can count them. Okay.
The one that you call it a 1.
1 to 2, yes, because it's input output. Yep. Other questions? Good. So this is kind of familiar to us, but now we're going to be looking at the physical size of the pitch diameter to do our comparison, as opposed to counting teeth when we're on a V belt. The other ones, though, sprocket, we can still count teeth if we have it available, or like I said, the synchronous drive. Okay, or we can compare what is my input to my output speed itself. Okay, the RPMs. Now, more equations. There are more things that we need to calculate to finish up our drive, but in the case of a belt drive, these are things that we would leave up to the actual vendor that we're getting it from. And Gates does exactly that for us. So when we specify what we need for our rotational speeds, input and output, and once we know what our center distance is, now Gates takes it upon themselves. They're going to now specify our sprocket diameters as well as the length of the belt. They do that for us. But the equations to do that are in the next section here. So we're going to take a peek at them, but we won't be using them for the problems that we're going to do. And this is very typical of belt manufacturers, okay? And I also want to stress that in many cases, what you want to do is you want to make sure that you are using a manufacturer's data, because if you're incorporating something into your design that could potentially fail, or even worse, potentially hurt somebody, you want to make sure that the onus is on them. So when we're specifying and I'm pulling in a V-belt drive, if I'm expecting it to last a certain amount of time, then I want to use how they tell me to design it, as opposed to me pulling out my book and doing it myself. Okay. You want to, because that way, if it does fail, or if it doesn't meet the life expectations, you can go back to Gates and say, hey, I went through your process and it didn't work. And then they're going to, say, okay, prove it. And then it's really on them rather than on you. If you use this, that's fine. You'll probably get numbers that are similar, but remember, whenever you're looking at incorporating a different manufacturer's data into your design, you need to then kind of use their process for sizing. That'll be the same thing. We talked about that a little bit for gears. It's going to be for belts. It's going to be for chains. It'll be for bearings. Anything that you would not be making yourself, chances are you won't be making, unless you're a bearing manufacturer, unless you're a belt manufacturer, you probably won't be making those. You're going to be incorporating them in. So that's why for this part, angle of wrap and the length of the belt, that's actually going to be set by the manufacturer, as we'll find out. I'll point that out when we get there, but the equations are here. So you'll notice that starting with equation number 5 here, this is going to be determining what your angle of wrap is. We'll talk about these terms, but we won't specifically calculate them. So angle of wrap is going to be how much angle of wrap do I have on either one of my pulleys. Okay. So you'll notice here that there's one for the angle of wrap on the smaller pulley and one for the angle of wrap on the larger pulley. Okay. The second one that we have here, this is going to be the length of belt that's on the wrap. So looking at, if you would, kind of the circumference length of how much wrap is on that pulley on one side and then on the other. Okay. And then lastly, we look at the distance from here to here and from here to here, which would be that same distance when these are horizontal, what that distance is. Okay. And by using the wrap on either side, that distance along, and then each one of those distances, we can get the full length of the belt. Okay. Now, when we have a belt like this, just like we have here, notice that this belt is continuous. Okay. This belt is continuous. There is no, I'm going to put it underneath here. I'm going to try to kind of show you guys. There's no place in here where I can take it apart, pull it apart, and then put it back together to put over the top of the V-belts. So that's why when they make a belt, they're not gonna say, oh, Kelly, you want a 46.2 long belt in its perimeter and its length. They're gonna make belts that are whatever the standard sizes are, and then they're gonna help you with matching up pulleys that are going to do it, and then what your center distance is going to be. And then you're going to find out, okay, what belt do I order then and incorporate it into my design. That's going to be the route that you take. So that's why I'm not saying that this isn't valid. You can calculate lengths of belts this way, but typically you're going to be getting the length of the belt from the manufacturer of the belt drive. Does that make sense to everybody? Okay. All right. So here we are on example number 7.1. This is going to be one of the practice problems that you're going to do for me. So if you want to grab out a piece of paper, this is going to be one that we're going to be doing by hand. We're not doing the whole problem. We're just going to do the kinematics part of it so we can practice using, those first, the velocity ratio, the angular velocity, and then also the linear speed of the belt. I want to make sure we have that under our belts, if you would, and that we're familiar with these equations. So we're going to look here at example 7.1. Example 7.1. Now, in this case, this is a synchronous drive. So the synchronous drive belt system is shown down here. It's a speed reducer. So that means coming in, our number one, our input is going to be the smaller sprocket. The larger sprocket is going to be our output. Now, in this case, they're telling us that our input shaft is going at 1,000 RPMs. And it has a 36 tooth sprocket on it. Okay. That's what we call a synchronous drive. That's when we have the belt that has the little like bumps in it, okay? The teeth, if you would. So we already know what the size of our sprocket is on our input, and then it tells us what the pitch diameter is as well. And then the output shaft over here is going to have 72 teeth going around and a pitch diameter of 7.218 inches. They're also giving us the center distance of 15.01, 15.01. So what they want us to determine, and the only things that we're going to do, we're not going to do this full problem. We're going to do the first three things. We're going to find out what is the velocity ratio, what is the angular velocity of the output shaft. So if this is rotating at 1,000 RPMs, our input, how fast is that output rotating? Right now, we don't know what its RPMs is, okay? So what is that W for the output? And then what is the linear speed of the belt? Okay, linear speed of the belt. And then the rest of them we're not going to worry about because again, that gets into stuff that we would get from an actual manufacturer. So as we look here, velocity ratio, if we go back just one page, you'll notice that we can calculate our velocity ratio one of three ways that they present here. So we want to look at the information that we're given and try to decide which one of these would be most appropriate. So we can do it with rotational speeds on the input and output. We can do it with the pitch diameters, or we can do it with the number of teeth. Now, which one can't we do here? The rotational speed, the W? Okay, why can't we do that? We don't have the output, exactly. We have the driving, but we don't have the driven. Okay, so this one we can't use. What other one can't we use? What is capital N? You look directly above, that's number of teeth, right? Now, we do have the teeth. Can we use that one? Yeah. What about the pitch diameters? Could we use that one? Either one, yes. So the one that we can't use, as BJ pointed out, is going to be the rotational speed here, okay? So now we look at our data and we decide which one we want to use. So which one's going to give us the best answer? Probably the teeth, right? Because when we find that pitch diameter, it's to 3 decimal places. I think they gave it to us. And it's probably rounded, okay? It's probably going to give us a very close answer, but yeah, number of teeth, because that's an integer number, I would use that. So let's look here at, let's identify this as example problem 7-1. And we're going to start our problem by just listing what we're given, okay? So what we're given is that our speed of our input, so we're going to call that W1, is 1,000 RPM. We know that the number of teeth, I'm going to kind of pull this down, maybe we can see at the same time. The number of teeth on that sprocket, we're going to call this N1, is equal to 36 teeth. Okay. And then the pitch diameter of that same sprocket, PD1, is 3.6099 inches. Okay. You always want to list your given information. That way you can kind of target, you know, what your next steps are going to be. We're also given on the output shaft our number of teeth on the output. We don't know what the output speed is, but that's gonna be something we're gonna find. So our number of teeth is 72 teeth. Okay. And our pitch diameter 2 is going to be 7.218 inches. And then we're also given the center distance C of 15.01 inches, right? Now, again, we're not going to finish the problem. We're going to just do the first three things. So we want to find, okay, our velocity ratio, our output speed, our W2, and then what was the last one? Oh, belt speed. So this is going to be our V of our belt, okay, which is that tangential speed from kinematics. All right, so we already identified for velocity ratio, we're going to use the number of teeth on the driven divided by the number of teeth on the driving, right? So step number 1, or part A, I think they're calling it, part A is velocity ratio. Velocity ratio, we're going to write our equation in variable form first. It's going to be the number of teeth driven divided by the number of teeth driving. Okay. Now, driven, driving. How can I remember the difference between the two? They sound very similar. Driving is going to be high speed, low speed. High speed. It's the driver sometimes referred to. Okay. Driven is the one that's accepting it, right? It's getting driven by. So that'll be usually your lower speed. Okay. When it's a speed reducer. So that means that the number of teeth on our driven is going to be the larger sprocket, right? And that's going to be our 72 teeth. So we're going to put 72 teeth in back. Don't just put 72, make sure you put your units here. And then our number of teeth on our driving. Okay, our driving is our small sprocket, and that one is 36 teeth. Okay. And I should correlate this on top. This would be our N2 and this would be our N1, okay, as far as the variables that were given to us. So what does our velocity ratio come out to be? 2? Yep, 72 divided by 36. Yep, it's a nice even number. It's going to be 2. And it's just that. Our teeth cancel out, right? This is unitless. This is unitless, all right? So put a box around. Part B. We want to know what is the angular velocity of the output shaft. Okay, we want to know what W2 is. We want to know what W2 is. Now, at this point, we aren't using it in the V equals R times W equation. So we're going to keep it in RPM format. Okay, so we know that the input RPM given in our problem said that our input was 1,000. And we now know what our velocity ratio is. So we should be able to figure that out, right? It's a 2-to-1 ratio. So if we look up here, right here, velocity ratio is equal to the speed of the driving divided by the speed of the driven, okay? So on the top is going to be our fast speed or low speed, or I'm sorry, fast or slow. Top is going to be faster. For us, it's going to be the 1,000, right? 1,000 RPM on top. And then the bottom is going to be what we're going to solve for. That's going to be our W2. So I'm going to put it in variable form first. Velocity ratio is going to be equal to W1 divided by W2. And then since we're solving for W2, I'm going to probably rearrange this before I put my numbers in. Okay. So I'm going to multiply my W2 up and I'm going to put the VR underneath. So W2 times VR is equal to W1. And then we're going to divide both sides by VR. So my W2 is going to be equal to W1 divided by VR. And then now I'm going to put my variables in place or my numbers. So up here, my W1 was 1,000. And then I just calculated my velocity ratio to be 2. So this is going to be 1,000 RPMs divided by 2. So my W2, as we can see, is going to be 500 RPMs. Okay. Make sure you put your units in all phases of the problem. Add the units here because I don't want them to magically appear in the final answer. Okay, I want to make sure that you set this up correctly, and having the units in here, canceling them out, ending up with the correct units lets us know that we set this up correctly. Okay. All right, any questions there on part B? Then the last one that we're going to do is just going to be part C. This is going to be the linear speed of the belt. This is going to be the V, okay? V. So the equation for V, we're going to go back a page. It's going to be V is equal to R times W. All right, so let's write that out. And this is, I think this is part C, right? Yeah. So part C, our equation is going to be V is equal to R times W. Okay, and I put a little flag on my V because that's, I don't know, that's my universal velocity V. Capital V to me is volume. Okay. Cursive V is velocity. You don't have to put the little tail on it, but that's how you'll see I do it. Now, we want to figure out what this is, and I'm just going to put belt underneath it because this is a belt speed that we're looking at. Now, before I even start filling in my values, what units am I expecting for a velocity? What would be typical units? Now, I'm in the English system here, right? We're dealing with inches. what would be units I would be expecting for a velocity? What was that? Feet per minute could be it, right? Feet per minute. What else? Inches per second. What else? No, we don't really need to, but you get the idea. It's distance, right? Whatever your distance is. And in this case, we're using a lot of inches. Distance, either per second, per minute, could be feet per minute. I'm going to peek ahead because I'm actually at a loss. I don't remember exactly what they did. Feet per minute. Yeah. Feet per minute is a very typical belt speed units. Okay. So we're going to use feet per minute. Okay. Now, when we look here, that means that when we multiply R and W together, we should end up with feet per minute. Now, the current units that we have inches, right? I'm just going to put my brackets around. And what are our units for W? Not the ones that we have right now. What do you have right now? RPMs, right? So you're ahead of me. We need to convert so that we can end up with feet per minute, right? We need to convert so we can end up with feet per minute. So we're gonna have to do a little bit with these numbers to get those values. Now, the first one we're gonna do is gonna be our W. We want to get our W in. Now, in the past, in kinematics, we would always go to, I think, radians per second, right? Radians per second, but we want to end up with our velocity in feet per minute. So we're not gonna put that into radians per second. We're gonna go to radians per minute. Okay. So let's do that conversion off on the side here. We know that we have 1,000 revolutions per minute, right? 1,000 revolutions per minute. Do not write RPM. You need to write this so that revolutions is on the top of our numerator and our minutes is in the denominator. Okay, so top down here. This is not a slash. Okay, because we're going to multiply across the top, divide by the bottom. So now we're going to get rid of our revolutions. So revolutions is going to go on the bottom, right? So 1 revolution on the bottom is equal to how many radians? 2 pi radians. Yep, 2 pi radians. There it is. Now, when I multiply across the top, I divide by the bottom, my radians cancel. So now I'm sorry, my revolutions cancel. I'm left with radians. So right now, my units are what? What's not canceled out? Radians per minute. Exactly. And that's where I want to be. So my W, this is W1, it's going to be equal to 1,000 times 2 times pi divided by 1. What's my number? What do you get? No, it's not 2,000 pi. What's my number?
6,283.
Would you?
Yeah.
That's okay. Yeah, you could do that. And then in the very end. So now I've got my, did anybody else get that same number just as a confirmation? I didn't plug it in. Okay, Brandon did, Eric did. Awesome. All right, so now we're going to use this number and we're going to plug it in up there. All right. Now, before we do though, do we have to do any other conversions? Our radius is going to be in inches because right now our pitch diameter is given to us in inches, right? So in the problem, I'm going to show you how you can do that conversion. That one's kind of easy. Okay, you don't have to do it separately. So we are going to put our radius in here first. So for our first, we're doing it for the W1 because we're going to be doing it for the radius one and the W1 because that's the rotational speed that we took, the 1,000 RPMs. Okay, so that means that we have to use the radius on that very same rotation. And the radius of that sprocket is going to be half of the 3.609, right? If the diameter, the pitch diameter is 3.609, then our radius is going to be equal to 3.609 inches divided by 2. That's our radius. Okay, that's radius number 1. And then I've got to go a little bit lower. Okay, so that's my radius number 1. Now I want to convert this right away to feet, right in my equation. And if you recall, when you guys, if you had me for kinematics or basic mechanisms, I would always do conversions with the vertical lines, right? Rather than the parentheses. Okay, and this is just to signify that this part is going to be a unit conversion. So to convert my inches to feet, I'm going to say 12 inches on my bottom, 1 foot on the top. And now this is going to be the value for that radius. Does that make sense? But now it's in feet because my inches would cancel top to bottom. I would still multiply across the top, divide by the bottom. So I'm going to take 3.609 times 1 divided by 2 divided by 12. Okay, while I do my equation. I don't have to do it just yet. And then I'm going to multiply that by my W1. I'm going to multiply that by 6,283 point, I think I got 19, right? If somebody said, and that's going to be radians per minute. Radians per minute. Now let's look at our units. You'll notice that my inches canceled and I'm left with feet. That's what I want. I want this in feet per minute. But why I've got that radian hanging out there. What happens with the radian? Jacob? What about Lucky Charms? They magically disappear. That's what they do. They magically disappear. So when I multiply feet times radians, they just go away, right? They just go away. So the units that I have left over here are my feet per minute. Okay, my feet per minute, and everything is nicely in that one place. So my V belt speed is what? So go ahead and do that. You should get 944.83 feet per minute. Okay. Don't forget to divide by 2. That one's an easy one to forget. So don't forget to divide by 2 because it's the pitch diameter divided by 2 to get that radius. Okay. All right. So kinematics. Remember it? Good memories? Fun to think back about? Okay, I'm right here, remember. It's all good. Okay. So that's the kinematics now. We are going to be taking this the step further, and we're now going to be specifying a belt drive with the corresponding sprockets that would go with it to achieve a center line. Okay. So what I'm going to do is we're going to be looking at our example, I believe, coming up here. Oh, no, not yet. Not yet. I am too eager to get to the example. There's a little bit in between here yet. So we looked at example 7.1, and now we're going to be looking at a little bit more specifics on the types of belt drives. Okay, types of belt drives. So there's a couple different types, and they're going to be based on the type of belt that you're going to be utilizing. So if we look at figure 7.7 on page 252, you're going to notice that there's a couple different styles or a number of different styles of different belt constructions in this illustration. Okay. Now, the one that we're going to be designing for, and that is very most popular, is going to be the wrapped construction V-belt design. Okay. And this is kind of like the run of the mill. That's going to be what we're going to be designing for using the Gates catalog. But a variation on that is going to be the one that we see over here. This is called a die cut cog type. Now, this does have notches, but the purpose of the notches in this type of a belt are not to engage with any teeth on a pulley. They are just to allow this bigger, chunkier, more stiff belt to make a corner on a smaller sprocket. Okay, that's what those are for. So these kind of look similar. This is a synchronous belt. This synchronous belt is intended to engage with the teeth, if you would, or sit down in the grooves on a synchronous pulley. Okay, but not this one. All right, so these two are similar. This one is the lighter duty. This one's like the heavier duty, okay, to make it around those corners. And then the synchronous belt We got examples up here. We won't be looking at a synchronous belt drive in this class. We just simply don't have the time, but the process is very similar. You would find a manufacturer, Gates as a manufacturer of synchronous belts as well, and follow their process to go through, okay? The next type is gonna be a V-band. And then we've got a another double V, and then we've got a poly rib belt. So these are just different configurations, and most often the differentiating factor is how much surface area do you have in contact with your pulley when you're looking at these, in order to either have more friction to, you know, allow more time before you slip, as opposed to less friction. Okay, and then also high and low profile. These are going to be a higher profile or thicker, where if you distribute that surface area over a larger distance, a larger line, if you would, then you can get low profiles as well. So there's a lot of different reasons you would use all different types of belts. Okay. Now, as we look at the construction of a kind of run-of-the-mill type of V belt, you're going to notice that it's going to fit down or snug down into the groove on the actual pulley itself. Okay. And then you can see the cross-sectional area here on how that works together. Now, the pitch diameter is strategically placed where we have these little circles here. Do you guys know what those little circles are? Anybody have any experience with that? The little circles, you see how the little circles are here? You see them there, and you also see them here. Yeah, well, it can be a number of different materials, but metal is a very popular one, where you have like steel through there, and that strengthens the actual tensile strength of the belt. And then in the inside, this portion on the inside, kind of the core, if you would, is going to be like a rubber. And then the outside is going to be a fabric. Okay, a fabric. You can kind of see that very same construction on these as well. So, so you'll notice the strategic placement of the little, like if we're dealing with steel, the little dots for the steel reinforcements going through. Why do you think it's there? Well, yeah. But
Wouldn't that be
notice
where you're
what it-
getting the highest tension?
Yes, and it's because of that pitch diameter. Remember we talked about pitch diameter? It's like the effective diameter. That's kind of where everything is concentrated. Notice that we've got like the V going up, we've got more surface area up there, but we also have strategically placed where our highest placement of the strength is in the belt. Okay, it's going to be placed there because that's where like the forces, if you would, are going through or transmitting through. Okay, or the torques are being transmitted. Sorry. Okay. So those are there, and those are there by design in that place. Okay.
What's the application of double angle?
You know, I can't think of one. That's a great question. Does anybody else in the room, or Ryan, do you have any experience with double V's? I can't think of where I would use one.
You put, like, rockets on either side. You could apply power to both sides.
I don't know if I don't recall that there was anything down in here, but that's a great question. Let me write it down. Yeah, the double V.
Seen it on like in the 80s and 90s, they used to have them on like they were serpentine belts for semis. Or at
Oh,
least I've
really?
seen a few of them.
Oh, okay. Has anybody else seen a double angle? BJ said he's seen it or seen the application on semis.
Oh, the double angle. I thought you were talking the double V. No, I haven't seen a double angle.
Yeah, double angle. I'd have to look it up. I think that's a great question. What was that? Oh yeah, if it gets wrapped around in different, maybe, yeah. Serpentine belts. I thought serpentine belts are more like this, aren't they?
Depends on how it's the other side.
Yeah, I guess so.
I
Okay.
mean, honestly,
Well, yeah, and it would be on the other side,
to
maybe.
get- Yeah, to get the amount of wrap. you need
Serpentine
on a lot
belt.
of Things, they'll tend to S.
That's true. And get on the other side. Yeah, okay. All right, that would make sense, I guess, with the construction. I've never seen them though. I've always seen just regular V-belts and synchronous belts. So, okay. All right, good, 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 good. Let's get back to our PowerPoint. Make sure we don't miss anything. I'm excited to do our example. It's gonna be the best part. Okay, let's look at belt installation. Okay, belt installation. What this is one of the pulleys has to move in order to get the belt over the top and engaged. So I don't know if there's an illustration. Of course not. Here's our example. Oh, it doesn't show one. Well, I'm gonna use this example as a. So I'm gonna go to figure 720. This is a little bit further ahead in our book, but figure 720, you can see this is a synchronous belt. And because this belt is continuous, okay, we can't like splice it, open it up and wrap it around and then re-put it back together. What we have to do is we have to allow on one side or the other for this to move closer so that we can get the belt wrapped around. And then we have to push it back to tighten it up. And then over time, what happens is these belts are going to stretch out just because of use. You have to have a way of tensioning that as well. Now, we're not going that far in this class with the design, but we will look in the catalog from our manufacturer, and they're going to specify for us what is the installation and what is the take-up value so that we can be sure that we incorporate that in the design at that point. Okay, so we are going to have that as part of what we specify for our drive, kind of finishing it up. So friction is going to be the cause of transmitting that power. As we said earlier, the tension force in that belt exerts a tangential force on the pulley, and that's how it gets applied to the drive shaft. Cross sections, we looked at those. One obvious advantage of a belt drive over a chain drive is going to be the noise. So if you can kind of use either one in an application, that might be a reason that you would want to go with a belt drive over a chain drive. Chain drives typically are going to be less expensive though. Belt drives are going to be a little bit more expensive. Okay. All right, here's our example. This is what I was looking forward to. So we are going to be now doing example 2 in our book. This is going to start on page 260, and I'm actually going to stop the video here, and then we'll start a new one for this example problem. So we'll get started over there. So I'm gonna